So here's the pendulum problem. So a student releases a 3.4 kilogram bob of a 2.08 meter long pendulum from the position shown, neglect loss. Okay, so the mass of the pendulum is 3.4 kilograms. And the length of the pendulum, this is important, is equal to let's see here, 2.08 meters. 2.08 meters. Okay, so that, I'm gonna put that out a little bit further out, just so we have that information clear. So the mass is 3.4 kilograms, and the length of the pendulum length is 2.08 meters. 2.08 meters. Now, what's interesting about that is we have a dotted line here. Well, actually, let's just draw a straight line. From here to here, where this is the position, height position of this H. Now, another thing to look at here, if you look carefully, is this length from here to here is equal to 2.08 minus H. Right? And this position here is irrelevant. We know that this is 2.08 meters. So now we have the hypotenuse and we have the adjacent side. So we could use something like, I don't know, cosine theta. So we could say cosine theta is adjacent over hypotenuse. So 2.08 minus H over 2.08. So if we multiply both sides by 2.08, so we get 2.08 times cosine, and here's theta, 29 degrees, is equal to 2.08 minus H. So our 2.09 times cosine 29, 2.09 times cosine 29 is equal to 1.828. 1.828. So 1.828 is equal to 2.08 minus H. So we're going to add H to both sides, and we're going to subtract 1.828 from both sides. So it's going to go away from this side. So that means H is equal to 2.08 minus that number, and that's 0.252. So 0.252 meters. So the pendulum's height above the lowest point is 0.252 meters, or 25.2 centimeters. Depends on how it wants to be recorded. So then what is the pendulum's maximum speed during the swing? Well, the maximum speed is going to happen at where H is, let me back that out. It's going to happen down here, where H is 0. Because here you have gravitational potential energy, and down here you have no gravitational potential energy, but you have all kinetic energy. So the kinetic energy at this point is equal to the gravitational potential energy at this point. So mgh here is equal to 1/2 mv squared down here. So if you set those equal to each other, 1/2 mv squared, so the m's cancel out. So the velocity equals, multiply both sides by 2, gets rid of the half, so now you have 2gh on this side, and you have v squared, so v is the square root of 2gh. H is this number. Take 2 times g times that number h, 19.62, and then take the square root of that, and you get 2.22. 2.22 meters per second. And then what is the tension in the string at the lowest point? Well, that's easy. The tension in the string, remember from centripetal force. Let me erase this kinetic energy notation. So KE. Okay, but right here you have a force pulling out, which is mg. You have a tension in the string. Tension in the string pulling in. So then the centripetal force is equal to the tension of the string minus mg, because this is into the circle minus out of the circle, right? Into minus out of. So the centripetal force is equal to the tension force minus mg. So that means the centripetal force plus mg is equal to the tension force. Now, centripetal force is mv squared over r plus mg is equal to the tension force. We know m, we know v, right? We just calculated v, and it works out to be 2.22 meters per second. So that's v, we got that. We know r because that's the radius of the circle or the length of the pendulum. So we know r, and we know m, we know g. So the only thing we don't know here is F sub t. So we can solve for the tension force by plugging and chugging. So what is the mass? Well, the mass is 3.4 times v, which is 2.22 squared, mv squared divided by 2.08. That works out to be 8.06 on this side. So if we scroll down just a little bit, 8.06 plus mg, which is 3.4 times 9.81, which is 33.35. 33.35. And then add that to 8.06, and you get 41.4. The tension force is 41.4 newtons. All right, there you go. Enjoy it.